For more than a decade, biologists have been able to turn stem cells into beating heart cells in a petri dish. And bioengineers have had some luck getting stem cells to grow on scaffolds to make simple, hollow organs like tracheas and bladders. But just how hard would it be to make a large, complex organ, like a heart, from scratch? Getting beating clumps of cells to organize into a three-dimensional heart requires scaffolding. At the Massachusetts General Hospital in Boston, Harold Ott and his team start with the scaffold that nature provides. They're using a technique called decellularization to strip away all the living cells from a heart. The owner of this specimen died only a few days ago. It will sit in this specialized vessel for about a week, while chemicals wash away its DNA, lipids, soluble proteins, sugars, and all other cellular material.
In a building, if you want to renovate it or repair it, you'd go in, you'd knock down drywall or get rid of cabinets and stuff like that. And basically we're going into the matrix and doing that. By perfusing solutions and detergents, we're getting rid of all the cells.
Afterwards, all that's left is a pale, white matrix of collagen and other structural proteins that once held everything together. Stripping away the donor cells removes the antigens that can cause the body's immune system to reject the new organ. The scaffold can then be repopulated with healthy new cells that are immunologically matched to the patient. The team hopes to one day completely reconstitute working hearts from a scaffold like this. But today, they're focused on how they might develop parts of the heart using the same process. They've taken a valve and part of the aorta from a decellularized heart and sewn it onto a cadaveric heart.
So this part here is the aortic root, including the aortic valve and the ascending aorta. And this has been decellularized, so this is a decellularized graft sewn onto a cadaveric human heart. And you can see here the right coronary artery button and the left coronary artery button sewn onto that decellularized graft. And the same thing here, this is the pulmonary artery and the right ventricular outflow tract here of the cadaveric heart. And this is the graft, the decellularized graft that has been sewn onto the heart.
Amazing. Harold and his team want to check if their graft would be able to do what these structures do in real life: prevent fluids from flowing back into the heart and feed oxygenated blood from the aorta to the arteries that feed hungry heart muscles. They use a CT scanner at the hospital next door to take a look at their work. Harold pumps contrast fluid through the aorta to check for backflow and to see if the arteries that feed the heart muscle leak. The team knew an emergency department case could come through at any time, so they had to act quickly.
Actually, scored a bit because you could do saline to contrast. Okay, good.
Back in the control room, Harold runs through his handiwork with radiologist Brian Goshadra.
And what we have here is a CT of this explanted heart, and you very nicely injected the aortic root, and we can see that you've sewn in your syringe to this area. Just to orient us, I'm really quickly going to put it into a 3D mode down here, and then window away so we can see what's left. And
Nice.
let's just blow that up. So
When you look at the sinuses of this aortic root, does that look physiologic to you? What does the anatomy look like?
it looks pretty close to what I would expect in a physiologic human. In this view, you can see it's very nice and smooth. So what matters most clinically is the inner luminal smoothness, and it really does look pretty good.
The process of decellularization and stem cell seeding could ultimately develop better replacement parts for the heart. These parts might prove more able to repair themselves and could theoretically grow with a young patient. To Harold, this technique could transform medicine.
Last night we were treating a patient who came in and developed sudden onset heart failure and is now currently on a machine that supports her heart and lungs. So seeing these patients and seeing that clinical need and these patients' families and understanding where all this research funnels into ultimately, which is helping patients and developing tools to improve lives of these patients in end organ failure, that's really what gets us going, I think, and what keeps us going.